In this lesson, we'll see how Euler's number e is defined, and we'll use it to define the natural exponential function. To derive the number e, we'll consider an amount that's invested with compound interest. Now, to make it easy, we'll have the principal amount of 1. The rate of interest is going to be 100%, which is 1. That means that after 1 year, the amount that we have has doubled. And the interest rate here is going to be paid only once at the end of that year, so our n, the number of installments, is only 1. So the value is given by the formula shown there, and in our case we have a principal amount of 1, the rate of interest is 100%, and the number of installments is 1, so that all works out to be 1 on 1. And again, the number of installments is 1. The time frame there is 1 year. So when we calculate that out, we'll have 1 plus 1 to the power of 1 is equal to 2. What happens if the interest is paid more often, let's say twice a year? Then we have 2 installments this time, so n equals 2, and everything else remains the same. So this now becomes 2. So we'll have 1 plus 1/2 to the power of 2. And notice that this time we have $2.25. We have more than what we had before because our interest has been paid in the middle of the year and we are earning interest on that interest. So if we keep going and have the interest paid more often, does that mean we're going to end up with more money? Well, you would think so. So let's work it out for 4 installments. So now our number of installments is 4. And notice that we have an amount there that's, again, bigger than the previous amount. And if we keep going with this calculation, will we eventually reach some limit, or does the amount just keep increasing up to infinity? So let's see if we can work it out for a few more values there. So we can see that so far we've worked it out for annually, semi-annually, twice a year, and quarterly. If we go to monthly, that means we have 12 installments. Our number has increased again. If we pay it weekly, we've got 52 installments. Our amount has increased again compared to the previous. If we pay it daily, then our amount again has increased. Hourly, it again has increased. And if we pay it every minute, you can see that the amount has increased again. Observe that as we go down this table, that the amount that it's increasing by is reducing. So does it reach some limit? What we're trying to find out is what does 1 plus 1 on n to the power of n become as the number of installments gets bigger and bigger and bigger. In mathematics, we write it as a limit. We want to see what that value is. As n gets bigger and bigger and bigger, it approaches infinity. And we can calculate that out, and it's approximately equal to that figure there. There's an infinite number of decimal places. It's not a rational number. It can't be written as a fraction. So we write it as E, Euler's number. Euler's number is very important in mathematics, and it's used as the preferred base for the exponential function and also for the log function. We'll see why when we study calculus. So the natural exponential function has a base of e, so it looks like that. We can apply dilations and reflections to that equation in both the x and y directions. So we'll put those constants a and k in, and we can also apply translations to get that equation there. But our base equation once again is that y equals e to the power of x, where e is that Euler's number, approximately 2.7. We've seen that Euler's number e is calculated by working out what 1 plus 1 over n to the power of n is equal to as n gets very, very large, and it's approximately equal to 2.7. The natural exponential function is defined as y equals e to the power of x, Euler's number e there,